Welcome to the 6th lecture of my series on the motion of a particle in a central force field. A quick recap of some of the previous results. First, the equation for the orbit expressed in polar coordinates, where we use the variable u, which is reciprocal of the radial distance r, turns out to be d2u d theta 2 plus u equals minus mu over L square into 1 over u square f of 1 over u. Here mu, of course, is the reduced mass and L the magnitude of the angular momentum. F of r is the expression for the magnitude of the force as a function of the distance from the center, and of course if we are dealing with a two-body problem, mu is given by m1 m2 over m1 plus m2, and in the case of a single particle of mass m going around a fixed center, mu would have to be replaced simply by the mass m. Now another very important equation which has been recast using u as the variable is the equation for the total energy. That works out to be L square over 2 mu times du d theta whole square plus u square plus capital U of r, the potential energy as a function of r, or you could write this entirely in terms of small u by writing that term as capital U of 1 by u. This whole sum is equal to the total energy E, which is a conserved quantity for the motion. Now over the last couple of lectures, we have been focusing on the Kepler potential, and we will be talking a lot more about this potential in the next few lectures. The potential is given by u of r equals minus k by r, where k is a constant. The corresponding force, which you get by taking its derivative and adding a minus sign, is given by minus k over r square. Note that the choice of this particular form has been done keeping in mind that we want the force to be attractive if capital K is positive. This can also describe the repulsive inverse square force simply by taking a negative value for capital K. Now, in the particular case of the Kepler problem, the orbit equation simply becomes d2u d theta 2 plus u equals minus mu over L square into 1 by u square times minus k u square, and as a result of the cancellation of the u squares on the right hand side, you end up with d2u d theta 2 plus u equals mu k over L square. This is simply the equation of a simple harmonic oscillator where theta plays the role of time and u the role of displacement, and it's solved rather trivially. And the solution, once you make a special choice of the initial direction, the direction from which the angle is measured, to coincide with the line joining the center of the force with the point of minimum distance from the center, the pericentron, the orbit equation simply becomes r equals r0 over 1 plus e cosine theta. Here r0 is given by L square over mu times k. So this does depend on the initial conditions, because L of course depends on the initial conditions, but as far as the radial equation is concerned, it's an overall constant which comes in essentially from this factor. E, on the other hand, depends on the amplitude, so to speak, of the solution of this harmonic oscillator equation and directly depends on the initial conditions for u. We will see later that E can be directly related to the energy of the orbit. That's something we are going to soon show. Now, in Cartesian coordinates, this equation can be translated to 1 minus e square into x square plus twice e r0 x plus y square equal to r0 square, an equation which is quadratic in x and y, and we spent quite a lot of time in the last lecture to explain why these equations essentially represent, for different values of E, different curves which are all conic sections. That is, curves that you get when you slice a cone with a plane. In today's lecture, we will begin with an alternative definition which will allow us to directly relate the polar coordinate version of the equation that we had obtained from the solution of the orbit equation to the conic sections. This definition is equivalent to the one that we have already given, that is, the curve that you get when you cut a cone by a plane. Showing, however, that these two definitions are equivalent is quite non-trivial, and the most beautiful proof of this that I know uses something called Dandelion spheres, and frankly the proof is really fascinating, but talking about them will take us too far afield in these lectures, so I would urge you to take a look at an advanced geometry book or maybe the net to find out details of how this definition is equivalent to the standard conic section definition. But now, first, let me talk about the definition. A conic section can also be equivalently defined as a locus of all points in a plane such that the distances from a fixed point bears a fixed ratio with their distances from a fixed line. There are too many fixeds in this particular definition, so let me just break this up for you a bit. Here we start with a particular fixed point, which is the so-called focus of the conic section, and a fixed line, something called a directrix. Our conic section is the locus of all points such that the distances from the focus and the directrix bear a constant ratio. Indeed, this ratio is what you call the eccentricity E of the conic section. So let's see a figure which shows the geometry of this. The fixed point is this one, the so-called focus. The fixed line is this line in black here, the directrix, and our point or points which make up the conic section is a point which is at a distance r from the focus, and the angle which the line joining the point to the focus makes with the perpendicular to the directrix is theta. We can use r and theta as polar coordinates for this particular point, and that's exactly what we are going to do right now. Now note that the distance r prime of this particular point from the directrix is easily related to this distance d, which is fixed, of course, the distance between the directrix and the focus, and these quantities r and theta. It's pretty easy to see that if you take away this distance, which is r cosine theta, from d, you get r prime. So r over r prime, this ratio, which as we have already mentioned, is the eccentricity. This being a constant gives us the equation r over d minus r cosine theta is E. And now you can easily rewrite that by multiplying this out and then moving all the r's to one side to get this. And this ultimately leads to r equals E times capital D by 1 plus E cosine theta. So we are back to our original solution of the Kepler problem, r0 over 1 plus E cosine theta. Note that although a direct proof of this definition being equivalent to the section of a cone by a plane definition for conic sections is a non-trivial one, as we have already mentioned, the way in which we have established all these should tell you that the two definitions are indeed equivalent. After all, we started with this formula which we had obtained as a solution to the Kepler problem, translated that to the Cartesian coordinates, and worked out the geometry of all this in the last lecture in some detail to show that an equation like this would definitely give you a conic section, by which I mean a curve which you get when you cut a cone by a plane. On the other hand, our other definition also leads ultimately to the same equation, r equals r0 over 1 plus e cosine theta. So, although directly showing that the conic section definition is equivalent to this fixed ratio definition, directly is a bit non-trivial, we have shown that both of these ultimately lead to the Cartesian version, which is a quadratic in x and y. So, via this indirect step of going via the Cartesian coordinates, we have actually shown the equivalence of these two definitions. Now, while the geometry of these curves, the conic sections, is a matter of great interest in themselves, our interest in these curves primarily lie in the fact that they are possible orbits for particles which are under the influence of the Kepler potential. Now, as such, it is also of great importance to figure out exactly which one of the conic sections a particular orbit is going to be. After all, an ellipse would give you a bound orbit, whereas a parabola would be just marginally between bound and unbound, and a hyperbola would correspond to an unbound orbit. Now, we have already argued before, using the effective potential, that for a Kepler problem, particles with negative energy will execute bound orbits. Those with positive energy would actually have only one turning point in the orbit, so they would essentially give you unbounded orbits, which are hyperbolas in this case, and just in between, we would get a situation where a particle has zero energy, which means that the particle would be following a parabolic orbit and would just reach infinity with zero velocity. Let us see whether these considerations based on the effective potential can be backed up by the formula for the energy that we have derived in the last lecture. Now, the expression for the energy in terms of u as a function of theta that we had derived earlier in the previous lecture turns out to take this form in the Kepler potential. L square over 2 mu times du d theta whole square plus u square, to which you add the potential energy term, which for the Kepler potential is minus ku. This is the total energy. Now, for the Kepler potential, the solution to the orbit equation, as we have already figured out in the last lecture, was u equals u0 into 1 plus e cosine theta, with the constant u0 being given by mu k over L square. Now, substituting this in the expression for the energy gives us the following. If you take the u0 square term common out from this bracket, you get L square over 2 mu u0 square. Du d theta whole square gives you an e square sine square theta, and u square gives you a 1 plus e cosine theta whole square. This is this particular term, to which you have to add the potential energy term, which for this solution is minus k u0 into 1 plus e cosine theta. If we now open up the terms in the brackets here, it's easy to see that this is going to be 1 plus e square sine square theta plus e square cosine square theta, so 1 plus e square. So these terms will be independent of the theta. And then you will have minus k u0 here again, another term which is independent of the angle theta. There will be theta dependent terms, however, but they must vanish at the end of the calculation. After all, the energy has to be a conserved quantity. It should not depend on where on the orbit you are. One theta dependent term comes from the square term here, the 2ab term in this perfect square. Thus, L square over 2 mu u0 square into twice e cosine theta. And another one comes from minus k u0 e cosine theta. And just by using the fact that u0 is given by mu k over L square, it's easy to see that these two terms cancel out, as they should. As I said, the overall expression for the energy must be independent of theta or u. It can only depend on the constants involved, L, mu, k, as well as u0. So after you arrange everything, especially noting that k can be substituted in terms of u0 using this, or you could substitute for u0 in terms of k. This is the expression that you end up with. Or now, if you just get rid of the u0 and bring in k, you get mu k square by twice L square into e square minus 1. So, the energy ultimately depends on mu, which is a constant for the given system, capital K, which again is a constant which describes the Kepler potential, L, which of course depends on the initial conditions, being the magnitude of the angular momentum. But more importantly than anything else, it depends on e square minus 1. And this immediately tells us that e square is given by 1 plus twice L square by mu k square into e. Hence, we can easily see that if E is exactly equal to minus mu k square by 2L square, which is actually the minimum value for the effective potential, as you can easily check, E square and hence E will turn out to be 0. Small e, that is. The eccentricity will be 0, so you will have a circle. If the energy is between minus mu k square by 2L square and 0, that is, it's negative, but not too negative, then this E square will be a value which is smaller than 1, leading to an eccentricity between 0 and 1, that is an ellipse. Capital E equal to 0 will give you exactly E square equals 1, an eccentricity of 1, which is the case for a parabola. And finally, if capital E is positive, you will end up with small e, which is more than 1, which is the case for a hyperbola. So our effective potential energy arguments is told us that energy was a determining factor in the kind of orbits you can get. Are checked out by this argument, you end up with the orbit being either a circle or an ellipse when the energy is negative, it's a parabola when the energy is just 0, and for a positive energy you get the unbound hyperbolic orbits. By the way, all these possibilities that I am talking about are valid primarily for an attractive Kepler problem where k is a positive number. If k were negative, then the potential energy would always be positive, and the effective potential, which has an L square by 2 mu r square term added to the potential energy, is also always positive, and hence the total energy cannot be negative, can only be positive, and there the only possible kind of orbit you will have is a hyperbola. So for a repulsive Kepler problem, the hyperbola is the only possible orbit. For an attractive Kepler problem, you can have any one of the orbits. Now that we are sure about the different kinds of conic sections that we are going to get under different initial conditions, which ultimately determine the energy and the value of L, let us take a look at the curves themselves in a bit more detail. And in order to do that, we will fall back upon Cartesian coordinates. Remember, we have started with r equals r0 over 1 plus e cosine theta and recast that into this equation involving x and y. These are, of course, Cartesian coordinates which have been chosen with the origin at the center of the force. Now, in order to see them in a bit more detail, what we will need to do is cast them in the standard form, where essentially you will have curves which are oriented along the axis and with the centers at the origin. So we will have to shift the origin and possibly also rotate the coordinate axis. But let's get one case out of the way first. The parabolic case where e is 1 is special because in that this term involving the quadratic in x just drops out and you end up with the equation y square equals minus twice r0 into 1 into x plus r0 square, which we can recast into the form minus 2r0 into x minus r0 by 2. Now it's obvious from this form that this expression is symmetric about the x-axis. Changing y to minus y does not change the curve. Here it's also easy to see that x can only be less than r0 by 2, can never go beyond that, because otherwise y square would have become negative. And this means that you have a parabola with its vertex at r0 by 2. The width of the parabola, which is described by a quantity called the lattice vector, is actually 1/4 of this constant sitting here, so that also happens to be r0 by 2. So the quantity r0 sets the scale for this whole parabola. Now with this parabolic case out of the way, let's look at the case where E is not equal to 1. And there, what we can always do is take the two terms with x together and use this to complete the square. So we can write this term as 1 minus e square into x plus e r0 by 1 minus e square whole square. Of course, this stays as y square. But on the right hand side, you will have to add to the r0 square that's already there, the square of e r0 by 1 minus e square times an overall 1 minus e square. So what gets added to the right hand side is e square r0 square over 1 minus e square, which easily simplifies to simply r0 square by 1 minus e square. Now this is the final standard form, which is curve case, after you divide through by the term on the right hand side. Now let me point out one thing. The original form of the quadratic might have told you that when e is more than 1, it is the x which comes up with a negative factor. While that's true, note that once we have completed the square to get this into the standard form, it's actually x which comes with a positive factor, not a negative one, whereas y has a factor which could be either positive or negative depending on the value of e. So now specifically if e is less than 1, this equation takes the form x minus x0 whole square by a square plus y minus y0 whole square by b square equals 1, where x0 is simply negative of this quantity er0 by 1 minus e square and y0 is just 0. There is after all nothing here with the y. A is the square root of this thing down here, so it's r0 by 1 minus e square, and b is the square root of this, that's r0 by square root of 1 minus e square. This is the standard equation for an ellipse whose center is at x0, y0, that is minus er0 by 1 minus e square comma 0, and whose semi-major and semi-minor axes are given by these quantities respectively. On the other hand, when e is more than 1, this factor would become negative, so you can no longer write this as y square by b square. You will have to write that as minus y square by b square. So then, our equation takes the form x minus x0 whole square by a square minus y0 whole square by b square equals 1. And now, x0 is given by er0 by e square minus 1. Exactly the same expression as before, but now this is the positive number, as opposed to this, which was a negative number. And y0 is 0. And what about a and b? These parameters which describe the shape of the hyperbola? Well, a is simply r0 by e square minus 1. Remember, a and b are positive by definition. So when I take the square root of r0 square by 1 minus e square whole square, in the ellipse case you had r0 by 1 minus e square, whereas for the hyperbola case, the positive number will be r0 by e square minus 1, since e now is more than 1. And b is the square root of this quantity with an overall minus sign added to it. So it's r0 over square root of e square minus 1. So these quantities tell us exactly where the center of the ellipse or the hyperbola is. Also tells us what the parameters a and b which describe the shape of the hyperbola or the ellipse, as the case may be, these things are. We will make a lot of use of these equations later on when we talk about the detailed properties of the various orbits. But for now, let me just focus on the elliptical orbits and try to figure out something more about the physics behind such orbits. Now, for the elliptical orbit in particular, we have r equals r0 over 1 plus e cosine theta, with e being between 0 and 1. Now, e is not strictly speaking more than 0, it could also be equal to 0 for the special case of a circle, which after all is an ellipse for which both axes are equal. Now, this quantity r0, as we have seen before, is given by L square over mu k, so this depends on the initial conditions. The quantity E also, as we have just seen, also depends on the initial conditions through the energy and the value of L. This is the expression we have seen before, and we can easily recast this to eliminate the L square in favor of R0 to this particular form, minus twice E R0 over K. This is an expression which will be quite useful in what is to come. Now, from this formula, it's obvious that R will take its minimum value when theta is 0, that is, when cosine theta has its maximum value, that is 1. Now that's not a surprise because we had decided when we wrote down this equation to essentially choose the line joining the center of the force to the pericentron, the closest approach position, to be the line from which the angle theta is going to be measured. So theta equal to 0, of course, should be pointing right towards the pericentron. And the pericentron distance Rmin is simply given by R0 over 1 plus E. The apocentron distance, on the other hand, the largest distance from the center, is obtained when cosine theta takes its minimum possible value, which is minus 1. So get Rmax equals R0 over 1 minus E. Note that because E is between 0 and 1, both Rmin and Rmax are positive numbers, as they should be. And of course, for E equals 0, Rmin and Rmax are both equal to R0, the radius of the circular orbit. Now it's easy to see from here that the ratio of Rmax to Rmin is simply 1 plus E by 1 minus E, and therefore E has a form which should be familiar from previous lectures where we had directly carried out the quadrature to figure out the equation for the ellipse. E works out to be Rmax minus Rmin over Rmax plus Rmin. So if you know Rmax and Rmin, you can actually calculate the ellipticity of the orbit from there pretty easily. A few alternative forms for this expression actually comes in handy. It's easy to see, for example, is that 1 plus E is simply twice Rmax by Rmax plus Rmin. So R0 can be written in terms of the maximum and the minimum distance as well. It's just twice Rmax Rmin by Rmax plus Rmin. 1 minus E, on the other hand, is twice Rmin divided by Rmax plus Rmin. So the product of the two gives you 1 minus E square is 4 Rmax Rmin by Rmax plus Rmin whole square. Now, this should not come as a surprise because we have already seen that E is given by this. So we take away E square from 1. This is simply a result of the simple thing that A plus B whole square minus A minus B whole square is 4AB. However, these expressions actually have their own utilities because they allow you to write the parameters for the ellipse directly in terms of measurable quantities like Rmax and Rmin. So A is simply Rmax plus Rmin over 2. That's the definition of A, the semi-major axis. And from the expressions of Rmax and Rmin in terms of R0, it's easy to see that this works out to be R0 over 1 minus E square, and this simply is given by minus K over twice E. This is the form which follows very, very simply from this expression. Therefore, the overall size of the orbit, the semi-major axis, essentially is determined by the energy of the orbit. On the other hand, the semi-minor axis, B, which is A into square root of 1 minus E square, can be easily seen after a bit of algebra to turn out to be square root of Rmax into Rmin. So while A is the arithmetic mean of the pericentron and apocentron distances, B just happens to be the geometric mean. We can also easily rewrite the two conserved quantities, energy E and the magnitude of the angular momentum small l, in terms of these geometrical parameters. From the equation A equal to minus K over twice E, it's easy to see that the energy can be written down as minus K over twice small a. So the energy is directly related to the semi-major axis. Of course, this expression can also be rewritten in the form minus K over Rmax plus Rmin. Similarly, using the fact that R0 is L square over mu K, it's easy to write L as root over mu K R0 or root over twice mu K Rmax Rmin by Rmax plus Rmin. And using the relationship between A and B with Rmax and Rmin, this can also be easily rewritten in a compact form as square root of mu K over A times B. So whereas the energy for a Keplerian orbit, a bound Keplerian orbit, is directly related to the semi-major axis of the ellipse, the angular momentum is related to both the semi-major and the semi-minor axis, and hence, whereas E determines the size of the orbit, L determines its shape. Now that we have gathered enough information about the geometry of the orbits, let us try to derive an important result once again using purely geometrical methods. This is a result that we have already derived earlier using dynamical methods. I am referring to a proof of Kepler's third law. Now, the geometrical approach to this is really rather simple. You start with the basic geometrical result that the area of an ellipse is given by pi times the product of its semi-major and semi-minor axis, pi times AB. Note that this is a direct generalization of the result that we have for a circle, where A and B are both equal to the radius r of the circle, and we end up with pi r square. You can think of an ellipse as what you get when you squash a circle down along one axis, and that's why the area has also been squashed by the same ratio to give you pi times A times B. Now, because of the fact that Kepler motion is central force field motion, we know that Kepler's second law holds. That is, the aerial velocity is a constant, and the aerial velocity is simply half of the magnitude of the angular momentum L over the reduced mass mu. And using our result for L, root over mu k over A times B, I can easily rewrite this as 1 over 2 mu times root over mu k over A times B, or half of root over k by mu A into B. Now, when I calculate the ratio of these two quantities, I get the time that the radius vector takes to sweep out one complete area of the ellipse, one complete period, which of course is nothing but the time period of the revolution, and the orbital period works out to be simply 2 pi root over mu by k, and what is important is the B cancels out, leaving you with A to the power 3 by 2 as the only shape dependent factor. And this can be rewritten very easily in the standard form of Kepler's third law. T square is 4 pi square mu by k over A cube. Now, we have already talked about the extent to which this can be treated as a constant in the case of a two-body problem, essentially stating that when a planet is much lighter than the central object, the sun, this mu can be replaced by its mass, and that cancels out from the g m1 m2 in the k, and leaving us with a pure constant which depends only on the mass of the central object. But we have already seen that before. So, we have given a proof of an essential dynamical result, the relationship between time period and the size of an orbit, in terms of what is almost entirely a geometrical argument.